Okay guys, so let's solve a problem here on shear concepts. So we have here a simple beam loaded as shown. It's a single reinforced beam with a depth of 540, a cover of 60 millimeter, and an area of steel which is 5,500 millimeters square. So we also have the material properties for Fc prime is equal to 20 megapascal, Fy is equal to Fb, which is equal to 276 megapascal. Okay, so your beam width here is not indicated, but it's actually 400 millimeter. So our units are all in millimeter, megapascal, and millimeter square. Okay. So we have a simply supported beam with 6 meters span, and the factor, the load WU, which is of course a combination of your dead load plus live load, okay, is already given. So we don't need to compute this because it's already directly given as to be 120. This is kilonewton per meter. Okay, so there's another correction there. So the required uh, values in the given problem is letter A, the spacing of the stirrup at critical section, which is of course a simply supported beam. This is at the distance. Okay. Uh, Spacing of stirrup at 1 meter from the face of the support. Uh, and also we are asked to find the point X from the support in which the stirrups are no longer required. Also, the point X from the support in which the minimum area of stirrups are required. And letter E, the minimum area of stirrups AB minimum, and the maximum spacing of stirrups. So these are code requirements, and these are actually some concerns on the diagram. So we will solve this using the diagram, and these two here are shear formula, no? So directly using the shear formula. Okay, for the first requirement or the first step on our requirement, we need to draw the shear and moment diagram. Okay, so how do you draw the shear moment diagram of a supported beam? So it's very simple. So the diagram constitutes a okay. We have here the shear diagram, which is like this, and the moment diagram, which is like this. Okay. So for the shear diagram, since this is symmetrical, we only need to get one half of the triangle here. Okay, so this is the triangle. Wherein the shear here, the maximum shear here is simply computed on the basis of the reaction, so which is W L over 2. Okay, so this is simply 120 times 6 divided by 2. Okay, so this is simply WL. So this is 360 kilonewton. Okay, so your triangle now is just like this one here. So we need to get the value of your shear at the distance. Okay, so what is this again? This is the critical section. Okay, and 1 meter from the support here. So is the requirement on the problem. So we need to solve for this by ratio and proportion. Okay, so we can solve for this and this by simply taking note of a ratio and proportion, or we can do it by a formula which is the shear equation. Okay, uh, so since this is a triangle, we can make use of a ratio and proportion here. So how do you solve for 295? So you just get uh, if this is a value, let's say y all over this length here is 6 minus what's your d? Your depth is 540. Okay, so this is y minus 0.54. 6 minus 0.54 is equal to 360 over 6. Okay, so you get y is equal to 360 divided by 6 times 5.46. Okay, so you get 295.2. Okay, so in order to solve for this, you make a proportion. So 6 minus 1 equals 360 over 6. So you just make use of a proportion and then by means of a triangle then. Okay, so you get y is equal to 240. So these are the requirements uh, brought up in the problem. Okay, so for your VVC and VVC over 2, so this answers your letter C and letter D later. So let's solve first for the moment. Okay, so what's the moment at this point here? So we already I already showed you how to get the moment here. Okay, so moment is simply the area here, the area of this diagram. Okay, so the area of this is simply the moment here. Okay, and the area of this plus the area of the green. Okay, so you add these two area will be the moment here. Okay, so 300. Okay, you can compute it by doing the area of a trapezoid. So 1/2 of 360 plus 295.2, okay, multiplied by the distance is 0.54. Okay, so you get the 176.9, and then to get the area of 300 here, you get 1/2 of 360 plus 240 times 1.0. Okay, so you get 300. Okay, so you just look into that because we will be using that on your computation for your VC. Okay, so here on the computation of the VC. Another way of solving your VUX is by using this formula. No? So you call this now the shear equation. So you can solve it by simply subtracting your VU max, which is WL over 2 minus W times X, where X is equal to 0.54 and 1. Okay, so this is 0.54 and 1.0. So you get the same value with that of the ratio and proportion. Okay, for your letter A requirement, we now solve for your critical section for shear using this formula. So you just substitute the value 1 over 7 square root of 20, then 120 times rho W, which is computed above. And then VU is your at D distance is 295.2, okay, times D is 0.54 divided by 176.9. So these are the pair of moment that you need, okay. This is the 295.2, the first pair, and the 176.9, okay. This is 240, the second pair, and 300. For sure, D is fixed to be uh, 0.54 here. Okay, so at critical section, your value is computed and it must be less than or equal to 0.30 of f prime square root of f prime cbwd. So this is the limiting value. If it exceeds this one, you use this value. Okay, so this is now our computation. So this is 221.42. Check if it is less than 0.3 square root of 20 400 by 540. So this is now 289.79. It's less than. So we are going to use uh, your VC that is computed here. Okay. Okay, for your computation for S, remember that our formula for uh, Vs is given by AVFY or AVFB. There's some missing parameter here, so there's a D here. Okay, AVFBD all over S, or you can make it this FY because FB and FY are just the same sometimes, but if not the same, then you use FB. Okay, so what happens here? So remember that our contribution for your total shear nominal is the contribution of concrete plus steel. Okay, so if we multiply this by let's say VVN must be equal to VU. So your VVN now will be phi times VC plus VS is equal to V. So your VU or VS can be computed by simply transposing VU over phi minus VS. Okay, so this is your formula for VS. This is V over phi minus VC rather. Okay. Okay, so if you compute it now, so 295.2 over phi. Okay, so this can be rewritten. This can be you can rewrite this by simply letting PVC there and then all over total over P, which is this formula here, or you can use directly this one here. Okay, so this is 295.2 VU minus 0.85. Okay, your fee for shear is fixed 0.85 if not given. Okay, and then multiplied by VC, which is 221.42 there. Okay, so you get the shear carried by the stirrup now is 125.87. And if you are going to solve for your S on the basis of this formula, if we assume a two-leg stirrup, so what's a two-leg stirrup? So this is a two-leg stirrup. Okay, so because you have two vertical legs, so this is called the legs. So two legs. Okay, so you have now a two-legged stirrup. So if this is 10, your area is pi over 4 10 squared times 2. Okay, so because you have a two-leg stirrup. So this is the number of legs. So you get 157 approximately. So S is equal to Vs all over AVFBD. Okay, so this is now Vs. Sorry, S is equal to AVFBD all over Vs. So this is AVFBD all over Vs. So this is in kilonewton. You convert it into Newton because this is in megapascal. So this must be consistent. Millimeter Newton megapascal will give you a 185.9 millimeter. Of course, the spacing must be chosen to a comfortable value for ease of execution. So you round it down. When you are rounding spacing, you round it down. Okay, round down to the nearest 12.5 millimeter or 1/2 inches. Okay, so this is 185. The nearest 12.5 mm here is 175 millimeter or 7 inches. Okay, or this 12.5 is 1/2 inch if you are using an inch unit, an English unit. Okay, for 1 meter from the face of the support, everything is the same. Only the difference is the values. Okay, so this is 1 over 7 squared of 20. So what changes here is your VU. Okay, this is your VU at 1 meter. Okay, and this is your MU at 1 meter. Okay, so this changes, but still your D is 0.54 and your BWD is this one. Okay, so this is 540 times, wala ito, 10 to the negative 3. You get 178 kilonewton, less than 289. So this is the limiting value again, which is 0.30 square root of F prime C BWD. Okay, so your Vs now becomes Vu minus VVC over Phi, which is now 240 minus 0.85 of 178, this one. Okay, divided by 0.85, we get 104.35. Using the same size of stirrup, two-legged. So this is 157 times 276, 540 divided by 104.35. You get 224.24 millimeters. So you round it again to the nearest convenient dimension, which is 212 or 212.5 millimeter or 8.5 inches. So that's how you solve for the spacing at critical sections indicated on your problem. Now, let's go to letter C and letter D. So this is a requirement on the diagram. So at what point are the stirrup no longer required? So for here, if we consider now your shear diagram, okay? So this is the actual shear diagram, and this is your, okay, actual versus capacity, okay, shear capacity. Okay, so what's the actual? This is the VU, and this is the PVC, okay? So the VU and the PVC has a point of intersection which is located somewhere here. This actually gives us point of intersection, gives us your X, okay, distance, which is the theoretical value at which the stirrup are no longer required. So we are now solving for this value from support up to this one. Okay, so how do you solve a distance of the point of intersection? We simply equate the two equations. Okay, so VBC and VU at x distance, and then solve for x and solve for the spacing. Okay, so how do you equate it now? So in this particular problem, I want you to do it. Okay, if the equation of VBC is 1 over 7, okay, square root of 20 plus 120 times 0.025. Okay, so what's your raw? Okay, so that's 0.025 of what? VUD over MU. So your VUD now becomes your VU at X. Okay, or let's put it a subscript. Okay, V at X times D all over M at X. Okay, so this is now equated to VU at X. Okay, so this is how you solve for your VUX. What is VUX? VUX is WL over 2 minus WUX. Or this is 120 over 2 times 12 minus 120 times X. Okay, and your MUX is simply equivalent to the area on this diagram. Okay, so what's the area of this diagram? So this is the trapezoid 1/2 360 plus VUX. So how do you simplify this? This is 6 times 120 is 7. 600 plus 120 is 720 minus 120x. Okay, so this is now 720 minus 120x. Okay, okay, times what's the distance? X. Okay, so you now insert VU there, you insert MU there, also you insert VU there, and then solve for X. Okay, so in the equations. So it's a little bit involved, but it's manageable. It's an exercise in algebra. Okay, for the letter D requirement, the only difference is that instead of equating VVC and VUX, you're equating VVC over 2 and VUX. So this is now your graph here will be 1/2. Okay, so that is your theoretical point or point of cutoff X. Okay, so it's the same procedure, but only this VC here is divided by 2. Okay, but the same procedure. So same procedure as in C. Same procedure as in letter C. Okay, for the AV minimum, you just use the formula here, which is 1/3 BWS over FB, whereas S value are the design spacing. Okay, so what are the design spacing? These are the spacing we use here. Okay, so this is the spacing I'm referring to, 212, and we have to check also uh, the other spacing, which is uh, 175. Okay, so 212 and 175. Okay, for the AV minimum requirement. Now for the maximum S max, I think it's not included in this lecture. Okay, so let's just continue. So this is for letter T and for letter F. Okay, the S maximum, you first have to check for VS. Okay, so what is your VS? Okay, your VS, you choose the smaller of the two. Okay, so you choose the smaller of 104.35 and the other VS is 125.87. Sorry, you choose the bigger. Okay, check um, for VS using, okay, choose the bigger because that's more critical, and the VS that is bigger is 125.87. Okay, and then compare it to 1/3 square root of F prime C BWT. Okay, so what is 1/3? If this exceeds 1/3 or is less than 1/3, then we choose okay, less than 1/3 square root of F prime C BWT. We choose S max is equal to D over 2 or 600, okay, millimeter. And if it is greater than 1/3, we choose S max is equal to D over 4 or 300 millimeter. Okay, so that finishes our problem on the requirement for letter C, D, E, and F. Okay, so I'll give you the exact values of this unknown on the next video. Okay, so you also try to solve it and then we compare notes afterwards. Thank you very much.